Hello everyone, I am Dr. Godandaraman. In this section we are going to discuss with formula unit 3 two-dimensional random variable. So two-dimensional random variable is nothing but two-dimensional random variable. Two types of two-dimensional random variable, discrete and continuous. Discrete and then continuous. So discrete two-dimensional is nothing but two-dimensional discrete random variable. The joint probability, so two-dimensional discrete random variable. So first of all, the two-dimensional random variable, discrete random variable is nothing but probability of Moss function for one-dimensional random variable. But here probability, joint probability Moss function. Joint probability Moss function is nothing but JPMS. So this is a joint probability Moss function is nothing but double in summation. So summation of probability of x comma y equal to 1. So y minus infinity to plus infinity and then x minus infinity to plus infinity. This is a joint probability Moss function. And mean, the mean of x, expectation of x equal to summation x into probability of x. So before that, because of here given the probability x comma y two-dimensional, but if you want to calculate mean single dimensional, therefore the two-dimensional change into single dimensional using the formula marginal probability function. Marginal probability function. So the marginal probability function of x, nothing but p of x, probability of x, p of x equal to summation probability of x comma y, the y range minus infinity to plus infinity. If f of x, p of x means y limits and p of y means x limits. So marginal function, marginal probability function of y. The p of y equal to small y, summation probability of x comma y is nothing but x equal to minus infinity to plus infinity. And then mean. So the mean is nothing but independent, even, conditional. So these are we are going to apply with the form. So this is a mean, expectation of x equal to summation x into p of x. X is minus infinity to plus infinity, and expectation of y equal to summation y from minus infinity to plus infinity y into p of y. If second moments x square means summation x square p of x, x from minus infinity to plus infinity, and y square summation y square p of y, y minus infinity to plus infinity. These are the first two moments, second moment. And the variance, so the variance is nothing but v of x, variance of x, x square minus e of x whole square, and then variance of y, expectation of y square minus e of y whole square. This is the variance of x, variance of y, and then independent and then conditional. So independent event for discrete. Independent event for discrete. Independent event. So if independent means probability of x equal to x, y equal to y, then probability of x equal to x into probability of y equal to y. This is the independent event. And then conditional probability. Conditional probability x given y. Conditional probability x given y. So when x given y, probability of x equal to x given y equal to y equal to probability of x equal to x comma y equal to y by probability y equal to y. This is a conditional probability x given y, and conditional probability y given x. Conditional probability y given x. So the y given x, y equal to y given x equal to x is nothing but probability of x equal to x comma y equal to y by x equal to x. So this is a conditional probability. And then joint. So joint probability. So two-dimensional continuous, two-dimensional continuous random variable. Two-dimensional continuous random variable. So the first one is joint probability density function. Joint probability density function, JPDF. Joint probability density function is nothing but double integration of f of x comma y dx dy equal to 1. The x range is minus infinity to plus infinity, y range minus infinity to plus infinity. This is a joint probability density function. And marginal function, marginal probability function, function of x. So marginal probability function of x, f of x comma y, when is given to find f of x or f of y. So this is a f of x. How to calculate? Integration f of x comma y dy. F of x means derivative dy, y minus infinity to plus infinity. And then marginal probability function of y, marginal probability function of y. So the marginal probability function of y is nothing but fy of y equal to x minus infinity to plus infinity f of x comma y dx. And then mean, expectation of x equal to integral minus infinity to plus infinity x into f of x dx, when the variable y, e of y minus infinity to plus infinity y into f of y dy, x square minus infinity to plus infinity x square f of x dx, y square minus infinity to plus infinity y square f of y dy. So this is the mean. And then variance, variance v of x equal to x square minus e of x whole square, variance of y, e of y square minus e of y whole square. This is a variance. And then independent event. When is independent, then f of x comma y equal to f of x, f of y. So this is a suffix xy, xy. And then conditional probability x given y, so f of suffix x given y, or to write the short form of f of x given y equal to f of x comma y f of y, and conditional probability y given x, conditional probability y given x. So this is the f of y given x equal to f of x comma y by f of x. And then covariance, because it will help to for correlation. Covariance of x comma y, equal to expectation of xy minus expectation of x, expectation of y. So this is a covariance of x comma y. Suppose, and then correlation, and before that if some results of covariance, it will help to using for MCQ, solving MCQ. Covariance of ax comma by is nothing but a into b covariance of ax comma by is nothing but a into b covariance of x comma y. Here xy two-dimensional random variable, so a b are constant, and then covariance of x plus a comma y plus b equal to covariance of x comma y, and then covariance of ax plus b comma cy plus d equal to a into c covariance of x comma y. These are some results. And then covariance of ax plus by comma cx plus dy equal to ac variance of x, bd variance of y, and then plus ad plus bc into covariance of x comma y. If the random variable x and y are independent, then expectation of xy equal to expectation of x, expectation of y. That's it. Covariance of x comma y value 0. So these are the covariance. And then correlation, Pearson correlation or correlation. Pearson's coefficient of correlation is nothing but r of x comma y, or rho of x comma y, or r suffix xy, whatever the notation we can apply with here, and covariance of x comma y by sigma x sigma y. Here covariance we know the formula, and sigma x sigma y is nothing but sigma x square root of variance of x, sigma y square root of variance of y. And then regression lines, regression so regression. So the regression is nothing but line of regression, regression, lines of regression. The lines of regression y on x, x on y. So x on y, the regression is nothing but x on y, x minus x bar equal to R is a correlation sigma x by sigma y, y minus y bar, and y on x, regression line y on x, y minus y bar R into sigma y by sigma x, x minus x bar, and then regression coefficient, regression coefficient is nothing but R equal to regression coefficient, correlation coefficient. So R equal to, this is a correlation coefficient, correlation R equal to plus or minus bxy into byx. These are the regression line. And then central limit theorem. Next topic, central limit theorem. Limit theorem. So the central limit theorem is nothing but if x1, x2 up to xn is a sequence of n independent and identically distributed random variable, each having mean mu and variance sigma square, and if x bar equal to x1 plus x2 plus up to xn by n, then the value of z equal to x bar minus mu by sigma by root n has a distribution that approaches the standard normal distribution, n tends to infinity, then provided the MGF exists. That's all. This is a central limit theorem. Then some of the form of central limit theorem, different form of central limit theorem. So one is Lyapunov form for central limit theorem. So here if x1, x2 up to xn a sequence of independent random variable with mean expectation of xi equal to mu I and variance of xi equal to sigma I square I1 to up to infinity, and if Sen is nothing but if Sen equal to x1 plus x2 plus etc plus xn, then under certain general condition Sn follows a normal distribution with mean mu equal to summation mu I from 1 to infinity, and variance sigma square as n tends to infinity. So this is the form of Lyapunov form. Then another form, Lindeberg-Levy form. The Lindeberg-Levy is nothing but if the random variable x1, x2 up to xen have the same probability density function with mean mu and variance sigma square, then the random variable Sn equal to x1 plus x2 plus up to xn follows normal distribution with mean n mu and variance n sigma square, that is Sn follows n into n mu comma n sigma square. Thank you.